We spoke about inertial trajectories, and we linked them to straightness. We said that, of course, if somebody's in an accelerated frame and you see an inertial particle moving, then you might see it with all kinds of jagged and curved motion and so on and so forth. But obviously we don't judge things from accelerated frames. We go into an inertial frame, then we look at another particle and we say, okay, it has a straight line trajectory. Then if it had a curved trajectory, of course, it couldn't be inertial. So could we take that as a good mapping, like inertia and straightness? Is that, anybody?
That sounds reasonable.
Sounds reasonable. Can you think of some objections? Try to destroy that hypothesis. Okay, can it map uniquely, one-to-one, unambiguously? So I'll give you, for example, one. There's several objections. One is that a stationary particle is inertial and it's just a dot. A dot is not a straight line. It's not straight. It doesn't have the geometric characteristic of straightness. So if a dot can represent the trajectory of a stationary particle, then we can't uniquely say that something has to have a straight line trajectory in order to be inertial. Okay, so I wouldn't map straightness to inertia. There are other objections. Can you think of something else? For example, you can have a linearly accelerated particle. The particle can accelerate along a line. It can even go back and forth, stop for a while, go here, go back. Each individual motion was a straight line, right? From here to here, from here to here, from here to here. Add them all up together, it makes one big straight line. And if you just drew a straight line like this, you would have no conception whatsoever what this particle was doing. In fact, it might not even need to be a particle. You draw a straight line on a graph, and it could just be the straight edge of an object. Also, there's so much information that's lost, obviously. We have no idea which direction it's traveling, right? If it's a straight line. Did it move this way? Did it move that way? Even if it was inertial. We have no idea of the speed. So there's a lot of things missing. There's an inertial particle that can be stationary, right, which is a dot. So the dot line objection can trouble us why we have to represent inertial trajectories in two different ways, and that's something we would like to overcome. We know, of course, from Galilean inertia, the indistinguishability, we can't really say that an inertial particle is stationary or moving, right? They're just moving relative to each other. So one person's dot is another person's straight line, another inertial system's straight line. So really we shouldn't distinguish between a dot and a straight line. So that any inertial particle's trajectory that is a straight line will be seen as a dot in its own rest frame. So there are many reasons why you would not map inertia and straightness. Now, somehow intuitively we think of straight and inertia, and I'm going to tell you that one could in fact map them well. And there is a hint in the very notion that we have of a trajectory being a straight line, because after all, if you think about it, the clue is in the very concept of a trajectory as a straight line. Because when you see a particle moving, do you see a straight line? Does anybody ever see a particle move and see actually a straight line? What happens is that your brain adds up all the individual perceptions, kind of like time-lapse photography, and turns it into a straight line. You don't see a straight line. Now, does that give anybody a clue? What is added into the picture by our brain? I kind of gave it away when I said time-lapse photography. We're adding in time. So in other words, if we add time into the diagram, as opposed to just a spatial diagram of a trajectory, we can overcome everything. Imagine that you have let's say I'll make the t-axis vertical, even though usually you see it horizontal, because in relativity that's the way we usually do it. So we're going to have, and I'm not talking about relativity yet, we have a t-axis, we have an x-axis. Okay, as time passes, it's going to be a straight line. How would you represent uniformly moving particles of different speeds? And the slope, or the inverse of the slope, if I have t this way and x that way, is going to be the speed. So every speed will be represented by a straight line at a different angle. So first of all, that's very, very nice, because we now can distinguish between inertial particle speeds as opposed to a trajectory line, which if we're just moving along the x, all of those would just be one straight line along the x. What about a stationary particle? Well, a stationary particle has a particular x value, wherever it is, here, let's say. As time goes by, it maintains that x value. So simply a straight line, we might as well start from the 0 point of the x, right, where the x and the t axes meet, and we'll make it along this line. In other words, a stationary particle effectively can be considered as having a straight line along the t-axis. Now, since any inertial particle, even if it's like this, in its own frame, will consider itself to be stationary, so every inertial particle really can represent itself like that in the diagram. Okay? But any other inertial frame will see it with some relative speed. So it's really not really relevant what angle we put, but it's nice that we can represent an inertial state as just a line along the t-axis, for example. That kind of, it's just a cute way of reminding ourselves what all these different things that we mentioned now. Now, if I draw this line, can it be the straight edge of an object? No, because what this represents is this location at this time, this location at this time, this location at this time. That's what this line, which is a set of points, each of these points represents a particular location at a particular time, a particular location at a particular time. So it represents all these locations at very specific times. So now we can see that we've overcome all the objections that we had before. We said that an inertial particle that's stationary has a dot shape as opposed to a straight line, even though you couldn't really distinguish one between the other. But here we find that we add time in, and we have the space-time diagram, that stationary and inertially moving, uniformly moving, have the same representation, a straight line. We also see that only being an inertial object, or stationary object, or a dynamic object, an object in motion and uniformly moving, can be represented this way. It can't be that this line represents just some straight edge of an object. And also we find that we have all this additional information. We know the direction that it's moving. It's moving along at time 0 for me. It was here, at time 1 it was here, at time 2 it was here. As opposed to if it was moving the other direction, we would have to have a line slanted in that direction, because it was moving at time 1 it was here, at time 2 it was here. And we know the speed. So it's a really, really nice, unique, unambiguous one-to-one mapping. Straightness and inertia, but we are required to have a t-x axis. And it could be curved, of course, if it's accelerated, but if it's inertial, it's going to be a straight line. A law of inertia, which we can now phrase as inertial particles have straight lines in this space-time diagram.